Hi, I'm DJ Ware. On this episode of the Cyber Gizmo, I'm going to delve into a little bit based on the short video that I did last week on Intel's forthcoming, I don't know whether to call it a chip or a chip complex. It's kind of difficult to really describe it, but it is the Intel, and this will be the Core Ultra, formerly known as Meteor Lake. And it's going to be brought to you today by my sponsors, both from Patreon and from the channel. And thank you to my sponsors for helping to bring this video to you. I'm going to let Intel explain this in their words, but I'll probably come back and comment a little bit on some of it as I see kind of fit to do that. But I guess the first thing that we always need to know is whenever there's a new product offering, so what? Well, yeah, what is the so what? If you can't answer that question out of the box, then most people are just going to lose interest in what you have to say.
We bring this age of the AI PC. We're thrilled by the momentum that we're seeing, and we're going to bring millions of AI-enabled PCs, ramping to tens of millions to hundreds of millions to enable tens of billions of TOPS of capabilities. And we're working with the industry and our OEM partners to make these sustainable, energy-efficient platforms. And the journey begins with our upcoming new Intel Core Ultra processor launch, formerly Meteor Lake. I'll probably goof it up one or twice in the keynote yet, but now it's the Intel Core Ultra. And we're excited because this brings a whole set of new capabilities, the NPU capabilities, and launching December 14th. And we're excited to have this in volume with numerous customers and partners.
The second thing is that Intel once is talked about the 4 key pillars that define what Intel Core Ultra is. And so, let's explore those a little bit and let Intel explain what their 4 core pillars were in the design of Meteor Lake.
There are 4 key pillars around which we define Meteor Lake. And we established these pillars several years ago at the outset of the program. And then they served as guideposts for us as we debated the feature set and capabilities that we would put into the product. First, we set out to build our most power efficient SoC ever. For many people today, battery life is as important as performance in their PC. And Meteor Lake will shine on both. Second, we envision Meteor Lake as the true entry of AI capabilities into the PC. And to that end, we built for the first time ever dedicated hardware in the form of our first AI engine, our NPU, into the silicon. Third, we set out to take a leap ahead in graphics performance, delivering the capabilities that people have come to expect in discrete graphics platforms integrated directly into our mobile PCs for thin and light laptops. And finally, we set out to launch our IA cores on our next generation Intel 4 process with our new P-Core Redwood Cove and our E-Core Crestmont for a major step forward in power efficient computing.
Next, what we'd like to do is I always like to start with a high level, and I noticed that so does Intel. There's, for those people that don't want to know all the nitty-gritty details, but they just want to know, what's this going to do for me? How is this going to help me in my daily workloads?
Let me introduce you to Meteor Lake, our next generation tiled architecture for client SoCs, built from 4 disaggregated tiles, assembled with our industry-leading Foveros 3D advanced packaging technology on our next generation Intel 4 process node. I'll walk through a really high-level flyby of the product, and then we'll go one click down and dig into the details. The first tile in our design is our compute tile. And this is the tile that contains our new E-cores, Crestmont, and our new P-cores, Redwood Cove. And we've made micro-architectural enhancements to both of those on Meteor Lake. And of course, this tile is built on our next generation Intel 4 process technology. The second tile in our lineup is what we call our SoC tile. And this contains many of the elements in our traditional Uncore. But on Meteor Lake, we've gone above and beyond tradition, starting with the introduction of new low-power island E-cores integrated into this tile and attached directly to the SoC fabric. These cores are ideal for an entire class of low-power workloads common in today's PC. They'll provide further power optimization while continuing to deliver performance in many workloads. This is also the tile where we've integrated our first ever AI engine, the NPU. And we've made advancements in our connectivity with next generation Wi-Fi and Bluetooth technologies, including support for Wi-Fi 6E and introducing support for Wi-Fi 7. First at the platform level, later on in the product family, integrated directly into the SoC. We've made significant improvements to the media and display capabilities on Meteor Lake as well, including support for 8K HDR and advanced AV1 codecs in our media block, and native support for the latest display I/O standards, including HDMI 2.1 and DisplayPort 2.1. This is also the tile where we've integrated the memory controller and DDR for communication with system memory. The new low-power island E-cores in the SoC tile represent our first major enhancement of the hybrid architecture that we originally introduced on Alder Lake. Together with the E-core and P-core in the compute tile, we call this our 3D performance hybrid architecture. And collectively, they'll bring our most optimized computing experience to PCs yet. The next tile in our lineup is our graphics tile. And on Meteor Lake, to make a leap ahead in capabilities, we, for the first time, took our Intel Arc architecture from our discrete graphics lineup and integrated it directly into this tile for performance in integrated thin and light PCs. And the final tile in our design is our I/O tile. And here we've integrated the latest I/O standards, including support for Thunderbolt 4 and PCIe Gen 5. The tiles in our design are assembled with our advanced 3D Foveros packaging technology. And this technology is a secret sauce that allows us to unlock the potential of a disaggregated architecture while continuing to deliver on the performance of a monolithic SoC. Taken together, never before have we implemented so many firsts in a single product design. From the new architecture capabilities, to the disaggregated construction of the design, to our next generation Foveros 3D packaging capabilities on our Intel 4 process node, you can see why we call this our largest architectural shift in 40 years.
But as you could probably guess, that's usually never enough, right? We always want to know more. Okay, so what? So you do this, you do that. Let's look at a little bit deeper and drill down a little bit into these 4 different tiles that are on this machine.
So with that high-level flyby, let's take a look at some of the major architecture changes we made to deliver on those pillars. The lofty goals that we undertook on Meteor Lake necessitated that we fundamentally rethink the way that we construct our SoCs. And to deliver on our most power-efficient SoC ever, we set out a series of 4 principles in our redesign. First, we repartitioned the computing-intensive IPs in the SoC to unlock further power efficiency while continuing to deliver on performance. Second, we re-architected the SoC fabrics for bandwidth scalability, delivering maximum bandwidth matched to system memory to all the major IPs in the SoC. Third, we made our first extension of the hybrid architecture introduced on Alder Lake with the addition of low power IA cores for further power performance optimization across a wide range of workloads in the PC today. And finally, we re-architected our power management flows to be able to handle all of the new capabilities that we packed into the product. So let's walk through each one of these principles and talk about what changes we actually implemented in the architecture to pull this off. In our SoCs that are in the market today, our media IP is embedded inside our graphics block. And our graphics block, in turn, is attached to a core complex. And this core complex contains both our E cores and our P cores. And all of the components in our core complex communicate with the rest of the SoC through a high-performance ring fabric. So that includes the cores, graphics, media, as well as the last level caches. And so any data transfer in or out of this complex goes through the high-performance ring, out into a system agent, and then on elsewhere in the SoC, or over to the memory controller and onto system memory. And this is a very high-performance solution. But it also means that for any component in this complex to communicate outside, a lot of content needs to be enabled and powered up. Take, for example, the scenario of video playback or streaming. That workload heavily uses our media block, but it's not a particularly intensive computing or graphics workload. But we have to power on the high-performance ring, the caches, and a lot of components to be able to access the media block in the SoC. And so this presents an opportunity for us. On Meteor Lake, we started by pulling the media block out of our graphics IP and embedding it directly in our SoC tile. And then we took the graphics IP and gave it its own tile in Meteor Lake. And now each of these blocks has independent attach points onto the SoC fabrics and to the rest of the SoC or system memory. The rest of our compute complex, we converted into a compute tile that's now a dedicated IA tile. And our high-speed ring fabric is dedicated to the IA cores within the compute tile. And so now, all of the major IP blocks within the SoC have independent attach points onto the SoC fabrics and can communicate with each other or system memory without having to piggyback or tunnel through any of the other IP on the design. And that means that we can now independently power on or off all of these IP, depending on the workload that's currently in use and whether or not they're active. And so if we go back to that video playback or streaming scenario, where media is highly utilized, so is display, and there are lots of memory transactions, you can see that we can just power on those IP that are heavily used while keeping the graphics tile and the compute tile off when they're not needed. And this provides us a much lower power operating point for these sorts of workloads. The second principle in our next generation Uncore is the re-architecting of our SoC fabrics for bandwidth scalability. For several generations in the PC, the bandwidth demands on the SoC have been steadily increasing. And this has really been driven by two trends. First, we tend to integrate more and new blocks into the SoC generation on generation. For instance, on Meteor Lake, we've integrated the AI engine for the first time, and that brings with it new bandwidth demands. The second trend is IPs that have existed in the SoC for multiple generations continue to get new capabilities and increased functionality. And those new capabilities bring along with them additional bandwidth requirements. Again, take media or display, for example, the support for multiple display pipes or the support for 4K monitors, 8K monitors, simultaneous 4K and 8K monitors, all brings with it new bandwidth demands. And that's resulted in traffic jams starting to be encountered in the information highway of the SoC, which is the SoC fabrics. Now, one way we could address this is by implementing dedicated side channels for the high priority blocks in the SoC and ensuring that they have on-demand bandwidth when needed. But this isn't really a scalable solution. So on Meteor Lake, we chose this moment to re-architect the SoC fabrics for modularity and scalability, implementing a new scalable SoC fabric with bandwidth matched to the maximum bandwidth of system memory and able to provide that to all of the major IPs in the SoC. At the same time, we grouped the I/O components together in an I/O domain, and we added an I/O caching agent, or what we call the IOC, that handles all the ordering requirements for the IOs, as well as address translation as information moves from the I/O domain to the coherent domains in the SoC. The third principle in our next generation Encore redesign was the evolution of our hybrid architecture. And to illustrate why we did this, let's go back to that video playback or streaming scenario. The repartitioning of the compute IPs to allow independent power up and power down was a major step forward for us in power efficiency in these workloads. But while these workloads aren't compute intensive, they still require a certain amount of computing to execute the workload. And that means that the compute tile, and again, the high performance ring fabric, the caches and everything on it, need to be powered up and powered down on a regular basis to access any of the computing elements in the complex. And so this presents yet another opportunity for us to provide lower power in this scenario. The addition of the new low power island E-cores in the SoC allow us to provide computing capabilities to those workloads that value the lowest possible power at sufficient computing. These cores are optimized for low power performance and sit directly on the SoC fabrics so that these workloads can be entirely contained in these cores and on the SoC without ever powering on the compute complex or the graphics tile. The major changes that we've made to our next generation Encore on Meteor Lake necessitated that we fundamentally rethink our power management architecture. There are a lot of new requirements in the Meteor Lake SoC. The power management flows need to be able to coordinate between multiple independent tiles. They need to be able to effectively manage major new IP blocks, such as the low power E-cores or the new AI engine. And to do this, we decided to re-architect from the ground up our power management architecture on Meteor Lake, starting with localized power management controllers, or PMCs, in each of the tiles on the SoC. These local PMCs are responsible for managing all of the major IPs within that tile. We also added PMCs to some of the major subsystems in the SoC tile. And then we have a system level power management unit that we call the P unit that's responsible for communicating with these local PMCs through simple, clean interfaces. And this is a much more scalable solution for the new capabilities we built into Meteor Lake, as well as for the capabilities that will come in future SoCs. The central P unit is also responsible for interfacing with system software and the OS, which now more than ever is critical to making sure that the right workload lands on the right computing element in the SoC for optimal power and performance. Taken together, the changes that we've made on our next generation Encore in Meteor Lake represent the heart of our most power efficient SoC ever. At the same time, we've addressed several of the scaling challenges to the future client SoC. And in the process, we've laid the foundation for innovation in the PC for the decade to come.
Finally, you have a fairly large piece of the architecture here, or a footprint, called the graphics tile, and that contains the Intel Arc graphics GPU. So what they were trying to do was to migrate enough of the discrete Arc GPU, that is the one that comes on a PCIe card, and migrate that onto each of these chips. So, and it occupies its own tile to do that. So let's take a look about how that works and what it can do for us.
We believe Meteor Lake will usher in a new era of the AI-enabled PC. And to that end, we've integrated capabilities into all of our computing elements in the SoC, including the GPU and the CPU, as well as the NPU. Our CPU will be ideal for single inference, bursty, fast response workloads, while our graphics IP will be ideal for periodic, throughput-intensive workloads like Stable Diffusion. And of course, the NPU will excel at low-power, sustained IA workloads. We set out to take a leap ahead on graphics performance on Meteor Lake, taking the rich feature set and capabilities that people have come to expect in discrete graphics platforms and integrating them directly into Meteor Lake. And to do that, we started with the integrated graphics IP that we have in our client lineup, and we scaled it up. And on top of that, we infused the feature set and performance of our Intel Arc graphics from our discrete graphics lineup into the IP. And the result is a new design optimization point for our graphics IP in Meteor Lake that we call our XE LPG graphics. The result is that for the first time, the architecture of our discrete graphics Arc is integrated into a thin and light SoC for clients. And we'll deliver the capabilities to provide up to 2x performance and 2x performance per watt versus our prior generation. Combined with the advanced feature set from our discrete graphics lineup, such as DX12 Ultimate and XeSS, and when paired with the new enhancements in our media and display components, such as 8K HDR and the advanced AV1 codec support, Meteor Lake will provide a truly leap ahead in graphics experience in the PC. The addition of the new low-power island E-cores in our SoC tile represents the first major enhancement of the hybrid architecture that we originally introduced on Alder Lake. We call this our 3D performance hybrid architecture. On Alder Lake, when we introduced the E-cores for the first time, they provided a major performance improvement for MT workloads while continuing to deliver exceptional performance in ST workloads with the P-cores. Similarly, the introduction of our low-power island E-cores on Meteor Lake will provide a major performance boost to a whole class of workloads common in today's PC that wants the lowest possible power at sufficient computing capabilities. With our 3D performance hybrid architecture on Meteor Lake, we'll deliver our most optimized computing performance to the widest range of workloads in the PC yet. Now, along with the increased capabilities of the computing in our PCs comes an increased need to tie together the hardware with the system, software, and OS. It's more important than ever to make sure that the right workload lands on the right computing element in the SoC, whether that's any of our IA cores or the graphics or the AI engine. And to do that, at Intel, we have a technology we call our Intel Thread Director technology. And it provides scheduling guidance and hints to the OS to make sure that workloads land on the appropriate computing engine. On Meteor Lake, we've made significant enhancements to this technology to ensure that the capabilities we built into the SoC will shine when the user is in front of their PC.
Finally, we get to Linux, and none of the talks really addressed Linux, although there was a lot of discussion in the Day 2 Innovation conference that just completed last week, where Intel's CTO was talking about, and he was talking specifically about Linux and how it was coming to help with enterprise workloads using, of course, their larger chipsets in Xeon. But what about this type of machine on either the mobile platform? Well, we can't talk about desktop because that's not coming until sometime in 2024. But we can talk about the mobile platform on laptops, which is currently released, is going to be released December the 14th in 2023. Now, one of the questions I have is that just the chip? Or does that mean there'll be laptops that'll be appearing on the market with those chips already integrated and installed? But what about Linux? Well, as it turns out, Intel has been working on the Linux kernel to put code that will support Meteor Lake in it since version 6.3. The first pieces that they worked on was, as you heard from the talk, media and the encode and decoding of various codecs was done in the graphics complex. Well, they moved that out and pushed it into the SoC. And so there's been a lot of changes that are needed in order for those codecs, like AB1, for example, to be able to process the workloads on the SoC instead of the graphics processor directly. So those changes went into version 6.3 of the Linux kernel. There's been additional things that have gone in. I'm just going to skip over 6.4 and talk about 6.5. So those added scheduling and performance patches that are based around the way Meteor Lake works, or Intel Core Ultra, if you prefer. So 6.6 has additional work in it. I don't have the release notes for that yet because the first release candidate just came out last week, and that is expected to release fully sometime at the end of October. Could be sooner, could be later. It just depends, again, how well the testing goes. So, yeah, you can't always pick a hard date, but, they do try to hit those dates as closely as they can. 6.7 has the graphics tile driver, and that's not scheduled yet. But if they hold to their normal, 2 to 3 months, or probably we'll see something maybe in December, definitely in January, that will have 6.7 in it. It just, again, they haven't even started scheduling work on 6.7 yet. I think I've seen some notes where they're doing some planning, but yeah, they won't until everything is done with 6.6, and that's all wrapped up. What do I think of all of this? Well, I mean, to be honest with you, I have not seen a CPU design this complex since working for Burroughs. And yeah, the mainframes and the supercomputers charted a lot of this ground years and years ago. But of course, that wasn't a micro design. It was a macro design where you had a lot of independent processors that were offloading various functions from the CPU, because some of the Burroughs mainframes were multiple processor, and they kind of worked in a balanced way of doing things where one of them assumed kind of the administrative control over the other one so that it would schedule work on both. And then there were all these other processors that were dedicated to doing specific types of I/O, like tape, card, print, networking, and communications, the old serial communications that we had back in those days, as well as being able to handle memory fetches and all of those kinds of things. There were controllers that were in the middle of that as well, in order to keep things running at about the same speed so that you didn't end up in a starvation or an overcommittal of the CPU. That's the two things you need to balance in order to get the maximum throughput. But if they can pull this off, they being Intel, if they can pull this off, this will be, there's a lot of different companies that are using chiplet designs. I mean, you probably remember when Intel made fun of AMD for doing it and calling it, using glue to glue the chiplets together. Well, Intel is essentially doing the same thing here. But in all honesty, it's a good approach. And it's a good approach because as the mainframe people learned, the more you can offload the CPU to devices that are doing work on their own, the more power you can provide to completing the application, because it frees up what the CPU is doing. The only way and only time CPUs benefit performance is when they're executing your code. If they're off waiting on an IO, that's wait time that, it's just idle. And you don't want that. You don't want idle processors, because those are costing you money and they're costing you time. So yeah, the busier you can keep those, the better off things are. The other thing is, if you can balance your workload, and we kind of got into that on one of the videos I did, or I started to talk about balanced and then got derailed by a problem that I saw, but I'll probably come back and start talking about that again. The act of balancing a machine is an art. It is an art form all to itself. So anyway, that's all I had for today. Hope you enjoyed this video, and if you did, please like and subscribe. Hope to see you all in the next one.